Section: Introduction. In this section, we discuss the advancements in diffusion models, which have excelled at creating high-quality images from text descriptions. Users often prefer these models for editing existing photos rather than generating new images from scratch. However, text-guided editing can be limited due to unclear language instructions and a lack of precise control over image features, such as the shape or position of objects. To address these limitations, we propose a more interactive approach to image editing that allows for intuitive actions like sketching, clicking, and dragging. Many current methods treat this interactive editing as a simple image-to-image task, relying on pre-trained text-to-image models. They typically require large amounts of training data to accurately reflect real-world changes, which can complicate the model and increase training costs. We reformulate interactive image editing as an image-to-video generation problem, where the source image serves as the first frame and an editing signal guides the creation of a video that includes both the source and target images. This new approach allows us to utilize real-world dynamics from pre-trained video models, potentially reducing the need for extensive data and computational resources. By focusing on the first frame for identity preservation, we eliminate the need for extra reference encoders, simplifying our model. We introduce FramePainter, which uses video diffusion models to enable flexible and precise image editing. FramePainter starts with stable video diffusion and incorporates a lightweight control encoder to add editing signals, like sketches, into the UNet. To improve handling of significant movements between images, we implement matching attention, which enhances spatial attention by extending it along the time axis, allowing for better correspondence between edited and source images. To validate FramePainter, we create thousands of image pairs from high-quality videos, ensuring they show significant object movement. We extract editing signals from these pairs, such as sketches and drag points. Our experiments show that FramePainter outperforms both training-free and training-based methods in terms of editing quality and consistency, while also demonstrating strong generalization to new scenarios not present in the training data. In summary, we reformulate interactive image editing as an image-to-video task and present FramePainter to facilitate effective image manipulation using video diffusion models. We also introduce matching attention to enhance the correspondence between images. Our results indicate that FramePainter achieves superior performance with lower training costs and excels in unfamiliar scenarios. Next, we explore related work in image and video diffusion models, highlighting their advancements and applications in generative tasks. Section Summary. In this section, we introduce FramePainter, a novel approach that reformulates interactive image editing as an image-to-video generation task, leveraging video diffusion priors to enhance flexibility and precision in image manipulation. Our method simplifies the model architecture and reduces training costs while achieving superior performance across various editing signals, demonstrating exceptional generalization to unseen scenarios. Section: Methodology. In this section, we describe our methodology for interactive image editing, which allows users to easily and accurately modify real-world images. We approach this task as one of generating video from images and introduce our tool, FramePainter, which leverages dynamic information from video diffusion models. To enhance visual consistency, we implement a technique called matching attention, ensuring that each edited image aligns closely with its original source. We treat interactive image editing as a process that mimics real-world changes based on user instructions, like sketching or dragging. Since videos capture how the world changes through interactions, they provide valuable guidance for learning these editing techniques. Traditional methods often rely on pre-trained image models and lack the dynamic context from videos, requiring many training samples and extra reference encoders for effective edits. Our approach, however, reformulates this task into an image-to-video generation framework, using FramePainter to address these challenges. FramePainter starts with a source image and an editing signal to create a two-frame video that includes both a reconstructed image and a target image. We utilize a lightweight control encoder to efficiently process editing signals, ensuring that these signals only modify the target image features, preserving the source image's integrity. Our model is fine-tuned using a diffusion loss that combines the source and target image features over time. To maintain visual detail, we employ two strategies. We integrate features from a clip image encoder into our attention mechanisms and combine the source image features with noise to feed into our denoising model. For achieving precise visual correspondence, we introduce matching attention, which enhances the connection between target and source image tokens. This method uses the target tokens as queries and the source tokens as keys and values, allowing us to capture detailed visual information. We also incorporate tracking results to refine our attention weights, ensuring that our model focuses accurately on corresponding tokens. Our overall learning objective combines the diffusion loss with a matching loss, which we control with a scaling factor. This approach allows our model to translate sparse editing signals into dense correspondences, improving the accuracy of the edits we produce. Section Summary. In this section, we reformulate interactive image editing as an image-to-video generation task using our model, FramePainter, which leverages video diffusion models to enhance visual consistency by matching attention between source and target image tokens. We train our model with image pairs and editing instructions from high-quality videos, allowing for precise manipulation of images while maintaining real-world dynamics. Section: Constructing samples from video data. In this section, we discuss how we construct samples from video data. Videos capture various real-world changes, such as object movements and changes in perspective, which help guide image editing tasks. To focus on manipulating specific areas, we select high-quality videos with a static camera for better data construction. Next, we sample suitable image pairs by randomly choosing 2 frames from the video with a time gap of over 1 second. We use optical flow predictions to filter out pairs with very small or very large flow magnitudes, resulting in a total of 22,000 image pairs. For extracting visual editing instructions, we utilize optical flow and tracking points from the target and source images. We design different algorithms for various editing signals. 1. For sketches, we apply a Sobel filter to extract edges from the optical flow. 2. For dragging points, we randomly select target points based on optical flow magnitude and find their corresponding source points. 3. For coarsely edited images, we conduct experiments. In our experimental setup, we initialize FramePainter with stable video diffusion version 1.1 and fine-tune it on our training samples for each editing signal. We set the training image dimensions to 576 by 1024 pixels and train the model on 2 A6000 GPS with a batch size of 4. The model undergoes 20,000 optimization iterations with a learning rate of 0.00001 using the Adam W algorithm. During inference, we use Euler discrete sampling with 25 steps. We divide our collected samples into training and evaluation datasets, with approximately 20,000 and 200 samples, respectively. The only difference in training for each editing signal is the signal itself, while the image pairs remain the same. Our evaluation benchmark includes source images, editing signals, and target images for a more thorough assessment of the edited results. To evaluate FramePainter's performance, we use 3 metrics. 1. ClipFid measures semantic alignment between edited and target images, with lower scores indicating better consistency. 2. LPIPS assesses perceptual similarity based on deep features, where lower values show closer visual similarity. 3. SSIM evaluates structural similarity, with higher scores indicating better detail preservation. In our comparisons with baselines, we present qualitative results showing that FramePainter maintains visual appearance and achieves more natural edits compared to Masa CTRL plus ControlNet. For instance, when removing a car door, FramePainter automatically updates the mirror reflection, ensuring visual consistency. The images refined by FramePainter also show more realistic details compared to those from Magic Fixup, which exhibit noticeable artifacts. Quantitatively, we find that FramePainter significantly outperforms state-of-the-art methods across all editing settings, even using only a fraction of the training data required by previous approaches. To further validate FramePainter's effectiveness, we conduct a user study with 100 samples, generating 500 edited images in total. Raters evaluate the images based on visual consistency, edit accuracy, and image quality, and we summarize the voting results. Section Summary. In this section, we describe our process for constructing samples from video data to enhance image editing tasks, utilizing high-quality videos with static cameras and extracting various editing signals through optical flow and tracking algorithms. We demonstrate that our model, FramePainter, significantly outperforms existing methods in both qualitative and quantitative evaluations, achieving superior visual consistency and structural integrity in edited images while requiring substantially less training data. Section: Emerging Capabilities of FramePainter. In this section, we discuss the emerging capabilities of FramePainter. Even though it was trained on only a few thousand samples from real-world videos, FramePainter has demonstrated remarkable generalization across various situations, especially in contexts that differ from its training data. We present several examples to illustrate this. Firstly, FramePainter allows for very simple editing instructions, enabling users to easily modify images. For instance, just 2 sketches can be used to move the antennae or close the eyes of a character. Secondly, it provides intuitive and precise control for more complex edits, such as adjusting the shape of flames or a horse's tail. Interestingly, it can also handle scenarios that were not part of its training, like enlarging a bird's beak or changing latte art into a heart shape. Next, we conducted an ablation study to evaluate the effectiveness of different attention mechanisms. Our findings, shown in the figures and tables, reveal that temporal attention struggles with large editing areas, while cross-frame attention can understand significant changes but has difficulty accurately matching image tokens, leading to inconsistencies in color. In contrast, matching attention enhances the accuracy of queries and establishes a strong correspondence between target and source images, outperforming both temporal and cross-frame attention in terms of metrics and visual consistency. We also explored the effectiveness of source image reconstruction. While many existing image editing methods focus solely on creating target images, our approach allows for the reconstruction of both target and source images. Our analysis shows that including source image reconstruction improves the visual coherence and realism of the edited images, as evidenced by better color and texture. The results also indicate that our method achieves lower scores in ClipFid and LPIPS, highlighting the benefits of source image reconstruction.